Welcome back to another Regents Physics topic overview. Today we're going to be working on projectile motion. So let's get right into it. Alright, so starting off with our facts here. The facts that I use in this video or go over in this video along with the examples are all going to be linked in the description down below as Google Docs. So you can follow along at whatever pace you like. You can pause the video at any point. You can jump to end of chapters if you like, just skip over things. Or you can jump to the first example and just skip over the facts as I talk about them. But starting off here with the X and Y components. This is an idea that was brought up in forces with two-dimensional forces. The same exact ideas apply for two-dimensional speed here. So any speed that is at an angle can be broken up into two components. Even if you have a speed that is horizontal, that's technically zero angle. It can still be broken up into its two components using these same exact ideas here. So the horizontal or X component is going to be the magnitude of my speed or velocity times cosine theta. So say I'm given 15 meters per second at an angle of 30 degrees. I'd have 15 meters per second cosine 30. Then my vertical component would be that velocity of speed times sine theta in that situation. So again, if I had 15 meters per second sine 30, that would be my vertical or y component of the velocity. And on the Regents reference table, these are on the back of the reference table in the form of ax equals a cosine theta and ay equals a sine theta. You just swap in a for whatever you have there. So if it's a force, you put in force for a. If it's a velocity, you put in velocity for a. Those are pretty much the only situations we're going to see things at angles. Alright, so let's move into our other facts here. Alright, so moving further into projectile motion. When an object is in free fall, two very important things. Its vertical acceleration is always going to be 10 meters per second per second. So again, acceleration is the change in speed of an object every second. That's why we say meters per second per second. Horizontal acceleration, that's always zero. There's a reason behind that. We'll talk about it with forces in a moment. Velocities in perpendicular directions add just like perpendicular forces. Talked about that on the previous slide. The magnitude of an object's velocity is known as its speed. So velocity is the actual direction. So if it's like positive or negative, if it's going east or west, the speed is just the number. So like the 10, if you have 10 meters per second, that's just the actual magnitude of it. And you can say like negative 10 meters per second or positive 10 meters per second or whatever it is. If you have 5 meters per second, direction adds that is going to be my velocity. When we do projectile problems, we're going to make kinematics charts for the vertical and the horizontal, and I'll have that as a part of the problems here. So let's move into the last of our facts. The projectile facts to know, my vertical speed, which is known as the y direction, at the maximum height is 0 meters per second. So that's just like going back to regular free fall when we weren't working in two dimensions earlier in the class. If we throw something upwards, at the max height, its speed was 0 meters per second. When a projectile comes back to the same height that it was launched from, it has the same speed that it was launched with, but negative velocity. So say I launch something with a speed and the y component ends up being 4.5 meters per second. My velocity there at the end, when it comes back down to the same height it was launched from, is going to be then negative 4.5. Just think of throwing something upwards. If you throw something upwards and it comes back down into your hand, whatever initial velocity you threw it with, it's the same exact speed, but it's just moving downwards instead of moving upwards. So now it's negative. Largest range, which means the horizontal distance. Projectile launched at 45 degrees to the horizontal. That's really an idea in Regents multiple choice questions that sometimes comes up. Same exact thing for this next bullet. Highest height or longest air time is 90 degrees to the horizontal. That should make sense. If I shoot something straight upwards, it's going to go higher than something that I shoot at an angle like 30 degrees. And then for the full flight of any object, the time that we get in the problem can be used for both the x direction and the y direction or horizontal and vertical direction. And that's important when making your kinematics charts. So let's get into our examples now. Alright, so again, if you happen to skip straight to the examples, all the examples and the facts that I talked about are in the description down below, so you can follow along with the video, and it's in chapters as you can see, so you can jump to any point in the video if you just want to see if you got the answer correct, if you were just working along with me. So in our first example here, if a ball is rolled horizontally with a speed of 15 meters per second off the top of a 2.4 meter high platform. The ball hits the ground below after some time, and we're going to neglect air resistance as we always do in Regents problems unless otherwise said. So in part A, the dot below represents the ball while it's in the air after leaving the platform. So that means it is rolled off the platform horizontally. Horizontally means that it has zero angle with respect to the horizontal. And we're going to draw all forces that act on the ball during this time. So an object, when it's in the air, when we're looking at forces on an object, all forces need to be made by something that is in contact with the object besides the force of Earth on the object, or later on in the course we do electrical forces. That one is also a non-contact force, but we haven't learned those yet. And it's not going to be unless we have very small objects and they specifically talk about electricity. So for this one, we're not in contact with anything. So that means that we are going to end up having just Fg. And Fg on Earth, the last time I checked, if I drop something, it's going to fall straight downwards. So I should have here a line that is straight downwards from my dot and Fg. And then Fg is the force of Earth, because again, that's the object that is creating that force on the ball. And again, that's it for all the forces, because there's nothing in contact with the ball. Our only non-contact force in mechanics is going to be Fg. So that's it for my free body diagram. What we should notice with this, though, is the direction in which my force is. That's straight downwards. There's no forces in the horizontal direction. That is the reason as to why we have zero acceleration in the horizontal direction, because there's no unbalanced force. There's obviously an unbalanced force in the vertical direction. There's nothing against Fg, so that's why I have a vertical acceleration, and it's always going to be downwards. So let's move into part B. Alright, so in part B, what is the direction of the ball's acceleration while it is in the air? So with this kind of builds on part A, and I kind of gave away the answer already for this. So if you look at my free body diagram, I had the ball while it's in the air, and it just had a force Fg going straight downwards on it. So then we can use facts from forces, and again, I'll have this in the description down below if you want to go check that out right now and find a fact that has to do with forces and direction of acceleration. If you want to do that, that's in Newton's second law, but you can look over the entire fact sheet. There's not a whole lot there to read through. So for this, I'm going to start off with that fact from Newton's second law. So if you want to go look at that, pause the video now and go to the description down below and get that fact sheet, because I'm going to start off here with the idea that I have acceleration is in the direction in which forces are unbalanced, and I can see that that is downwards here. So starting off with my fact of physics, an object's acceleration is in the direction in which forces are unbalanced. So that's going to be my evidence here that is going to help me find out my direction of acceleration. Then I'm going to have my reasoning based on this. So I'm going to say, since the object's forces are unbalanced downwards, or the direction in which the forces on the object that are unbalanced are downwards, that's going to be my reasoning. Since the direction in which forces are unbalanced on the ball is downwards, I can then make my claim, which is my answer, that the acceleration is also directed downwards. And this again should make sense, because I have acceleration in the vertical direction. That's against my motion. If I throw something upwards, it's going to come down, and it's going to slow down to a stop at its highest point. But there's no acceleration in the horizontal direction, which is a fact of physics. So that's going to be my claim there. So let's move into part C of this example. Alright, so in part C, we're going to create a kinematics chart for both the horizontal, the x direction, and the vertical y direction. We're going to fill in what we know based on the facts of physics and the actual question above. So to talk about the facts of physics, what we're always going to have both the horizontal and the vertical direction is the accelerations that we already know. So that's what I'm going to plug in here first. So look at the horizontal direction, I look at my fact sheet. Again, these facts are in the description down below. And I see that the horizontal acceleration is always 0. You can put meters per second afterwards, but it's not going to matter all that much. So 0 meters per second because 0 is 0. Then the vertical direction. I know that the vertical acceleration is always 10 meters per second. So I'm going to put this in there as well. These are the first two things I'm always going to have when I make my kinematics chart. This actually start off any projectile question, no matter what. And if they don't tell you to do this, they're not going to tell you to do this. This is just because we're learning it for this video. But otherwise, not going to tell you to do this. Make them fill in what you have based on the question and the facts of physics, and you're going to be set up really well to answer anything they ask you to find. So what else do we have here now? Now we're going to be looking at the actual question, because the only two things that we know every single time here. So your ball is rolled horizontally. So horizontal means that it has no angle with the horizontal, meaning the angle is effectively 0. I'll come back to that in a second. With a speed of 15 meters per second. So both the x and the y direction, we can do our components for them. And again, I have this on the fact sheet. My x component is v subscript x equals the velocity they give me cosine theta. So I'm going to put this in here. You might be asking yourself, since there is no angle, why am I doing this? I just want to show where these things come from. You don't always have to do this with horizontal projectiles, but it kind of also just makes really no difference between horizontal projectiles and launch projectiles. Kind of gets that idea going for both of them. So then we're going to plug in the speed that we have here. The speed is given to us in the question as 15 meters per second. We then have here cosine of whatever angle is. This one again is horizontal. So if it's horizontal, that means it's 0 degrees with respect to the horizontal. So we have here 0 degrees to plug in for my angle. And when you plug this into your calculator, or you may just know this, that cosine of 0 is actually just 1. So essentially 15 times 1, and that's going to leave me with an initial horizontal velocity of 15 meters per second. Then in the vertical direction, we're going to do essentially the same thing, but if you look on your fact sheet or on the reference table on the very back, you know that it's going to be with sine instead. So we're going to have my velocity that they give us times sine theta, then plug in the velocity as 15 meters per second times sine of, again, this angle is going to be 0 degrees because I have 0 degrees with respect to the horizontal. It's a horizontally launched projectile. And then if you know that sine of 0 is 0, you can do that, or just to make sure, you can plug it into your calculator, and sine of 0, just to make sure, is 0. So anything multiplied by 0 is going to be 0 meters per second. So that's why some teachers may just tell you this straight away. That's where it actually comes from. Again, horizontally launched projectile is 0 degrees with respect to the horizontal. That's why I get 0 meters per second for my initial vertical velocity. And whatever the speed they give me in the question for something horizontally, that's going to be my initial horizontal velocity. Now, the other thing they give us in the question, they say that we are on top of a 2.4 meter high platform. So height is that the vertical or the horizontal direction. Last time I checked, height is up and down. That's going to be the vertical direction. So my distance here in the vertical is going to be 2.4 meters. And that should be everything we are going to have both the x and the y direction. Again, this is a very good practice to do for any kinematics question you want to make a chart as well. But any projectile question, you want to make the chart for both the horizontal and the vertical direction, because now we can see that on the vertical side, I have 3 out of 5 variables, so I can find either final velocity or I can find time. And on the horizontal direction, I actually do have 3 out of 5. I forgot here that I have 0 acceleration, so I need to put in here that my final velocity is also 15 meters per second, but that's not really going to help me much at the moment. So we can move into part D of the question, and I'm going to bring this kinematics chart over so you don't have to write it out over and over again. Alright, so in part D, we're going to calculate how much time the ball was in the air for before hitting level ground. And we're going to show our work, including the equation and substitution with units. Actually, just making our kinematics chart is going to allow us to be able to get part of the points here, if we're able to pick the right equation, of course. Because we already have our numbers written out here with the units next to them. So that actually, along with the equation, gives us 1 point here in this question if it was a part 2 on the Regents. So now it's just which direction are we going to end up using to figure out the time. If we look at the horizontal first, we have 3 out of 5 variables, which means we could do that. But if you use the horizontal direction, since we have the same initial velocity as the final velocity, because my acceleration is 0 meters per second per second. Again, acceleration is a change in speed every second. So if that's 0, I have no change in speed throughout. If I use an equation with the horizontal, say like the final velocity equation to find time, I'm just going to go in circles and everything's going to end up canceling out. So really can't do that. The vertical direction, though, looks pretty promising, as we have an initial velocity, we have an acceleration, we have a displacement, and we're trying to find the time. So it looks like we can use the vertical direction here. That's going to be my question mark. That's what I'm looking for. So based on this, what equation am I going to end up using if I have displacement, I have acceleration, I have initial velocity, and I'm trying to find time? You'll look on the reference table and see which equation is going to line up with these variables. And the equation that does is going to be what I like to call the displacement equation. So as d equals VIT plus 1/2 AT squared. So with this first, I'm just going to solve for time algebraically. The other thing I'm going to do is plug in any zeros that I have to cancel that stuff out. But I'm going to just solve for the t by itself here. So my initial velocity is 0. So VI times t here. Anything times 0 is 0. So that goes away. So I'm left with d equals 1/2 AT squared. And I just want t all by itself on one side of the equation. So we're just going to get rid of what's attached to it. So the first thing I see attached to it is, or the two things that I see attached to it here are 1/2 and a by multiplication. So in order to get 1/2 away from the a and t squared, right now it's really just like at squared over 2. So the opposite of that is going to be multiplying 2 on both sides of the equation. So on this side, it will cancel. And I'm going to have 2 times d is equal to at squared. Then my next step, I have a times t squared. Doing the opposite of multiplication is division. That will cancel out a on the right side and bring it over to the left. So we're left with 2 times d over a equals t squared. And then, of course, the last step here is going to be the square root of t squared, because the opposite of squaring something is taking the square root of it. So I'm going to be left here with 2d over a, or the square root of 2d over a, is equal to my time. Now I'm just going to plug everything in and get my answer. So again, 1 point here for the Regents is just having the numbers written out like I have them in my kinematics chart, and then the equation. That's sufficient for equation and substitution with units. Then at the end here is just my answer with the units. So what I have here, I'm going to just substitute with units anyways. So I have the square root of 2 times 2.4 meters, because again I'm using the vertical direction, over my acceleration in the vertical, which was 10 meters per second, and that is equal to time. So from here, this is just straight up plugging into the calculator. I'm not going to go through all the steps here. What I like to do is kind of break this up into each part. So what I'm going to do is 2 times 2.4 on the top to get a number there, which is going to end up being 4.8. Divide that by 10 on the bottom, and I'll get 0.48 for inside the square root. Then take that square root and get my final time, which is going to be 0.69 seconds. So my time here is 0.69 seconds, and that is the answer for the time in which the ball was in the air before hitting level ground. So let's now move into part E. Let's move into part E of this example. We're going to calculate the horizontal distance d. The ball travels from the edge of the platform. And of course, we're going to show all work, including the equation and substitution with units. So for this again, look at the horizontal distance. So we're going to use the horizontal part of the kinematics chart. This is going to be my question mark here, the thing that I'm looking for. There are a few equations that could jump out to you, but there's only going to be one that actually is going to work. If you use any other equation besides the displacement equation, the d equals vit plus 1/2 at squared, you're just going to run the problems. Because you have the same initial velocity as you have final velocity. So any equation with both of those means that you're going to end up essentially just canceling everything out, and you're not going to get an answer at the end of the day. So we're going to use this equation here. D equals VIT plus 1/2 AT squared. The difference between this part, when you're trying to find a horizontal distance, and in part D, where we're trying to find just the time, is that instead of having my initial velocity as 0, I have my acceleration as 0 for now the horizontal direction. So that means the whole 1/2 AT squared term is going to be canceled out, because anything times 0 is 0. So over here, this cancels, and I'm just left with d equals VIT. So now I can just plug in what I've been given here, what I found, the initial velocity of 15 meters per second, and my time of 0.69 seconds. And I'm going to end up here then with my final answer, which is going to end up being, so 15 meters per second times 0.69 seconds. When you plug this into the calculator, you're going to end up with a horizontal distance d of 10.35 meters. So that's going to be my final answer. And I've essentially finished the puzzle in the horizontal portion of the kinematics charts. So again, for this, my 2 points, writing out everything on the side here like I have it in the kinematics charts, along with my equation. That's 1 point. Then just doing the math to get to the answer. My answer with units is my other point. So let's move into example number 2. Alright, so looking at example number 2, a child kicks a ball from ground level with an initial velocity of 8.5 meters per second at an angle of 35 degrees with the horizontal, as shown in this diagram below. The ball has a total time of flight of 1 second, and we're going to neglect air resistance as we always do unless we are told any different. The dot below represents the soccer ball while it is in the air after being kicked. Draw all the forces that act on it during this time. So just a free body diagram in part A. So very similar to my first example, we're going to have the ball that is in the air. There's nothing touching it. So only non-contact force in mechanics is the force of gravity, Fg, the force of Earth on the object. And last time I checked on Earth, if I drop something, it's going to fall straight downwards. So this force is going to be straight down, and that is Fg. And again, when doing a free body diagram, we label what the force is, or the objects that are exerting the force on each other. So this is the force of Earth on the ball. Alright, so that's the only force that is on the ball at that point, because there's nothing in contact with it when it is in the air. Again, this shows that my acceleration is only in the vertical direction. There's none in the horizontal direction because there's no forces that are unbalanced. So let's move into part B. Part B kind of keys off of part A, looking at my free body diagram and determining what is the direction of the ball's acceleration. So we know from forces, and again, this fact sheet is in the description down below if you want to take the time right now to look at the facts for forces and see what the direction of the acceleration should be based on that. So for this, we know that in forces, that acceleration is in the direction in which forces are unbalanced. So how I'm going to start off here with this explanation is that fact of physics. So that is my evidence here. an object's acceleration is in the direction in which forces are unbalanced. That's again my evidence or my fact of physics. Now I'm going to explain this with my reasoning. I'm going to say that since my forces are unbalanced, or the forces on the ball are unbalanced in the downwards direction, or something similar to that, since the direction in which forces are unbalanced on the ball is downwards, we're going to then make our claim that my acceleration is also directed downwards. So the ball's acceleration is also directed downwards. Again, that should make sense because I have a vertical acceleration. I do not have a horizontal acceleration because I have no unbalanced forces or forces that are unbalanced in the horizontal direction. So let's now move into part C. Let's take a look at part C here. We're going to create a kinematic chart for both the horizontal and the vertical direction and fill in what we know based on the facts of physics and the question above. So we always know for both the horizontal and the vertical direction is going to be my acceleration. So again, this is straight from our fact sheet. My acceleration in the horizontal direction is always going to be 0. And I'm just going to write this out as 0 meters per second so we know we're talking about the acceleration and just get used to writing out those units. Then in the vertical direction, we are going to have 10 meters per second. And for this situation, since I have an initial velocity that's going upwards, and we know that my acceleration is directed downwards, I have to make one of them negative if I want to, say, find the maximum height. So I'm going to make this acceleration negative. All right, so then we're going to plug in what we have based on the question. In the horizontal direction, we are then going to start off here with, we have an initial velocity of 8.5 meters per second and an angle of 35 degrees with the horizontal. When we have the horizontal direction, we're going to have to use our x component, and that is going to be my velocity v times cosine of theta. Then we're going to plug in this velocity here. So this is going to be 8.5 meters per second times cosine of the angle that I was given, which is 35 degrees. Then we're just going to plug this into my calculator. So 8.5 cosine 35, that is going to be 6.96, and that is meters per second for my units for velocity. Then what else do we have in the horizontal? I have no acceleration, so that means that my initial velocity is going to be my final velocity. Then my displacement, we do not know yet, and my time of flight is 1 second based on the question. So that's everything we know in the horizontal direction. We can move into the vertical. So for the vertical, my initial velocity, again, that is going to end up being my y component. So the difference between this and the x, we're going to use sine instead of cosine. So my velocity times sine theta, we're going to plug this in here as 8.5 meters per second times sine of the angle, which is 35 degrees. And then when I plug this into my calculator, 8.5 times sine of 35 is going to give me a velocity of 4.88 meters per second. Then my final velocity, so for the entirety of the flight, is going to be the negative of my initial. So this one's going to be negative 4.88 meters per second. But at my maximum height, it's going to be 0. So I'm going to put in parentheses here 0 meters per second for max height, just because we might find that helpful later. Then my displacement, we don't know quite yet. In this situation, that's going to be used to find our max height. In that way, you're going to have a situation in which you have different heights for launched projectiles or projectiles at an angle greater than 0 in Regents Physics. Then my time here is going to be 1 second. And again here for my maximum height, that time is going to be half the time for the full flight. So this one is going to be 0.5 0.5 seconds for max height. All right, so for this, we can then move into the next part of our example, which is going to be part D. All right, let's take a look at part D. We're going to find the maximum height reached by the ball, and again, show our work including the equation and substitution with units. Since height is going to be in the vertical direction, that's up and down, we're going to use the y portion or the vertical portion of my kinematics chart. So for this, I have my initial velocity, I have my final velocity at this height, I have the velocity at this height, I have my acceleration, and I have the time it takes to get to this height. So that means I can use a couple different equations. I can either use the timeless equation, which is vf squared equals vi squared plus 2ad, or I can use my displacement equation. I'm going to use the displacement equation because I really don't have to do any algebra with this manipulating anything to get d by itself. D is already by itself on one side of the equation. So I'm going to use, again, d equals vit plus 1/2 at squared. All right, so from here, I'm going to plug in what I know, my initial velocity. So I don't have to do any algebra at this point. So my initial velocity is 4.88 meters per second. The time it takes to get to the max height is 0.5 seconds. That is then plus 1/2 my acceleration, which has to be negative, otherwise I'm not going to get the correct answer. So negative 10 meters per second. And again, this time to get to the max height is 0.5 seconds. So I'm just going to do this in multiple steps here, so mistakes aren't made with my algebra. So we have 4.88 times 0.5. That's going to give me here 2.44. And with units canceling out, that's going to end up being meters over here. Then we're going to have plus on the other side, a plethora of things. So 0.5 raised to the second power, that's 0.25. 1/2 of 10 is 5. So we're going to have on the other side here, negative 1.25. And again, that's going to be meters just based on how all the units there shake out. So we should have here 2.44 minus 1.25, and that's going to give me a maximum height of 1.19 meters. So that's my max height there, just plugging in everything that I have from the vertical portion of the kinematics chart, and I'm going to get my answer there as 1.19 meters. So let's move into part E, the final part of this example and of the video. So moving into part E, we're going to determine the total horizontal distance the ball travels before it then returns to the ground. So for this, we're going to use the horizontal portion of our kinematics chart. What we have here is everything besides the distance. So that's going to be my question mark here. And then I'm going to go ahead and find an equation that will allow me to find this. So you may be saying the timeless equation, which is the vf squared equals vi squared plus 2ad. But that's just going to lead me in circles because I have the same initial velocity as final velocity. I have a zero acceleration. That's just not going to end up working. So I'm going to use the displacement equation. So d equals vit plus 1/2 at squared. In this equation right now, my acceleration is 0, so this whole 1/2 at squared term is going to go away, and I'm going to be left with d equals vit. And if you're noticing what's going to happen here, it's going to be a fairly simple calculation because now all I have to do is just know what to plug in. My initial velocity was 6.96 meters per second. My time is 1 second. And then when I multiply these, obviously anything times 1 is then itself. So I'm just going to put this over here. My distance is going to be 6.96 meters. All right, So that's the last part of this example and of the video. So I hope these examples were helpful and see you guys in class.